Welcome. Basically, I will talk about some performance improvements in Flink, and I will try to convince you to enable this feature as soon as it lands in the mainline, so you can enjoy some performance benefits. So there is a paradigm shift in big data platforms lately. Long ago, it used to be that most of the overhead was the I/O in big data applications, so the CPU wasn't really the bottleneck. Most of the time was spent on network or disk read and write. But these areas in the meantime evolved, and CPUs became increasingly a bottleneck. So right now it makes sense to utilize this resource better as well. And even when an application is I/O bound, we can reduce the costs by reducing the load on the CPU, because this way we might consume less electricity. Serialization in Flink is a very central concept, because it is not only used for input and output, but Flink also operates on serialized data. So changes to the serialization has a very fundamental effect on the whole system. And Flink supports several serialization methods, including cryo. And Flink has its own serializer as well, which is the most efficient of all, not to mention the default Java serialization. Although there are still some room for improvement, so that made this Google Summer of Code project possible. So this graph shows the result of some benchmarks, and as you can see, using the Flink serialization can result in a better performance than using cryo, and which is very important on this diagram, is that it is even more efficient than using Java objects. So basically Flink working on the serialized formats instead of Java objects can improve the performance. Okay, so let's look at what can we improve in the Flink serializers. Where is the room for the improvement? And one of the most important thing to note here is that the code is very hard to optimize for the JVM, and it is not specialized for certain types, but the Flink serializer is a general code that works for different kind of classes. So basically one of the inefficiencies that, for example, in the Pojo serializer, is that fields are accessed using reflection, and that has a very significant cost. And also, we access fields in a loop, and in each iteration, we might dispatch to a different type of serializer, and this inhibits inlining, so the JVM cannot substitute the implementation of the serialize method into the loop body. Also, there are some null checks and null and subclass flags involved, even though when we are working with primitive types that cannot be null. And we also try to deal with subclasses when we are dealing with the final Pojos. And we also cannot really unroll this loop easily, because the upper bound of this loop is not a compile time constant. So basically, the problem is that this code is great for generic use, but there is little specialization that the JVM can do for a certain class so for this code to be efficient. It is important to note that Flink has several serializer-based innovations because the central role of serialization in Flink. For example, it is, as far as I know, unique to Flink that serializing methods has object reusing overloads to avoid excess object creation. It has a very delicate type system that can provide us very useful information about the types that we would like to serialize. And what this talk is about, we will be able to generate very specialized code that can overcome the inefficiencies that are inside the current Flink serializers. So basically what I did was I implemented runtime code generation, and I was focusing on plain old Java objects because the serialization of plain old Java objects involved a lot of uses of reflection, and eliminating this reflection was a huge performance boost. So this was the best return of investment. And using the type information that the Flink type system provides us with, we can generate very specialized code that do not have reflection, that do not have redundant null checks or subclass handling for primitive types. It do not have subclass handling for final types, and it can unroll loops. And this can enable the JVM to do additional optimizations at runtime. I used Janino as a runtime compiler and FreeMarker as a template engine for code generation. So before talking about the results, I would like to survey the group. So who has already written a custom serializer in order to improve the performance of a Flink application? Who has written a custom comparator to improve the performance? Yes, that's much more rare because it is much harder to write a custom comparator for a type because it depends on what are your keys. And who used tuples instead of Pojos only to increase the performance of a Flink application? Yes, there are quite a few people. So it will be over soon. So after the code generation is enabled, the performance, so you no longer need to use tuples only to get better performance, but you can use your preferred coding style and achieve the same performance. And I also would like to ask who wants performance that is very close to tuples, but you can still have null values in your objects. There are also a few people. Okay, so let's see some numbers. I could say that we have a 6 times performance improvement, but of course, when I say that there is a 6 times performance improvement in the serialization speed, that does not mean a 6 times performance improvement in the rest of the Flink job. So in order to be able to say something useful, we should measure some real-world Flink application. One of the applications that I did a benchmark with is a Nine-Mans Morris application that calculates game theoretical values of game states for this game. It is an iterative job, and it does a lot of different kind of operations. So this is a very complex application, and it has a heavy use of plain old Java objects. And it is great that the generated serializers did not explode under this kind of workload. So I also use some other applications to measure performance. For example, the reduced performance test and the word count Pojo. Of course, these are much less complex applications. And I did the measurement on my local machine, and I also did it on a cluster. And the results were consistent. And here they are. So basically, what you should see here is that when we turn on the code generation for serializers and comparators, we get about 20% performance improvement. And even when we do handwritten serializers and we turn on the code generation for the comparators, we get a bit better performance than the handwritten serializers with the default comparators. I will talk about what is left to get the performance of the handwritten serializers, and what is the reason for this gap. So basically, in order to get to the same performance level than the handwritten serializers, we need to be smarter about predicting what will be the how many bytes long will the serialized format of the object. And also, it would be great if we would be able to do some conceptual flattening, so we can actually inline the serializers that our serializer call. So instead of trusting the JVM to do this, we could do this at code generation time, and it can provide us with a significant performance improvement. And also, the generated serializers includes in the serialization format some flags to tag whether an object is null or whether it has some, or whether it is a subclass of its static type. And also, these fields are available for, so these tags are available for all of the fields for the plain old Java objects. And this is a very significant overhead. Unfortunately, because the serialization format is not versioned right now, I wasn't able to change the format. So in order to preserve the backward compatibility, at least for now, I did not change the format. Also, in case we can better handle the primitive types, we can inline their serialization instead of calling the int serializer and the other serializers for primitive types. We can avoid a lot of boxing and unboxing, and this is also a very significant performance improvement. And unfortunately, the Janino compiler in some cases might generate a bit slower code than the Java compiler in the most common JDKs, so there is also some room of improvement there. So I'm gonna walk you through how this all works. And during the implementation, I stumbled upon some very strange results that at first looked like black magic to me. But fortunately, in the end, they always had some logical explanations. And I would like to share some of this adventure with you. So let's look at how serializers work in the traditional way before the code generation was introduced. So when we have a plain old Java object class, there is a type extractor that will generate the type info object that contains a lot of information about the type. And this type info object will create a new object, a serializer. So it will just instantiate a class with a certain arguments. And this class will be able to serialize the object of the original objects of the original Pojo class. So let's look at how is this changed during the code generation, when the code generation was introduced. So the type information is the same as earlier, but instead the type info will not generate the serializer, but it will invoke a serializer generator that will read some templates that has the skeleton how the serializer code should look like, fill in the missing gaps, and then it will pass the code to the Janino compiler. And the Janino compiler will create a class loader. So what a class loader is, it is basically something that can load a class. In JVM languages, we always load the classes using this class loader. In the most common case, this class loader loads classes from jar files, and it knows the class path, and it do the class loading based on a name lookup. So what Janino does, it creates a new class loader that can only load the class that it was just compiled. And using this class loader, we can load the class, we can instantiate it, and generate a serializer. And this serializer will be able to serialize the Pojo objects. Okay, but there is one thing that might be unexpected to some people. The way Flink works, serializers need to be serializable. So when the job manager creates the plan for the job and it sends it to the task managers, it also sends the serializers. So that's one of the reasons why it is important to be able to serialize the serializers, because serializers are sent over the network just as other objects. So one of the first challenge was, how can we load the code that we just generated? Because when we deserialize a stream that contains a class, an object, the first step is to load the class of that object. But we have several class loaders because each time we compiled. So each time when we compile some code with Janino, we can get a new class loader. So we have as many class loaders, as many classes we compiled with Janino. So we need a way to actually choose which class loader to use. And in order to solve this issue, we had to come up with a custom class loader that basically dispatches the class loading to the corresponding class loader that can load the generated class. So that was the least arcane issue. The next challenge was that what should happen when we have multiple nodes or JVMs. In big data applications, this is the case most of the time. So it's definitely a use case that is worth to support. So basically, when we compile a serializer on one JVM and we send the serializer to other JVM, during the deserialization, we need to load the class of this serializer, but that class is not available in the JVM that received this serializer. So what can we do? There were several attempts to solve this issue, but what worked in the end, we wrapped the serializers in a wrapper, and the wrapper contains not only the serializer object, but also the source code of the serializer. So basically, now, if we send the wrapper over to another JVM, the JVM looks up the source code from the wrapper, it compiles the source code, so it will have a class, and it can instantiate it, and finally we will have our serializer on the other JVM. So great, let's try this solution out. And when I did so, I got a class cast exception that the JVM wasn't able to cast a class to the same class. And it was a bit surprising, but as it turns out, the Java language doesn't use a real nominal type system. So in order for two types to be the same, it is not enough that they have the same name. It is also required that these two classes are loaded with the same class loader. So basically, if we load the same class with two different class loaders, then those two types are different. So in case we recompile the source code of the serializer each time it is deserialized, we each time create a new class loader. So we each time create a new type that is different from the one that we had before, even though they have the same name. So it was kind of surprising. So one possible solution would be to cache the compiled class, compiled class and the class loader, because if we compile the class only once, then we have only one class with this name, so we will not have this problem. So let's try this out, and unfortunately this time we get a different class cast exception, but this has a very similar nature. So the problem is that, as it turns out, each time when a task is started, Flink will generate a new user class loader. So when we compiled our serializer, we use the user class loader that is different from the one that is created when a new task is started. So the same user object that the generated serializer knows about and that the application actually uses will be two different type. So in order, this was also very surprising, and in order to solve this issue, I had to invalidate this cache each time a new user class loader is created. So basically, too little caching is bad, too much caching is also bad. So the trick was to find just the right amount of caching that will give us the correct behavior, that all the class loaders of the users and all the class loaders that the Genino generates are in sync all the time during the lifetime of the Flink application. And fortunately, this time it worked, and I was able to run non-trivial applications using the code generation method on clusters. Actually, there was a couple of more challenges. I also encountered some bugs in the runtime compiler, and also the Scala interoperability was kind of a challenge. And the generated code is harder to debug because by default there is no file on the disk that you could read the source code, so it is harder to step into debug the generated code with the debugger. Okay, so what should we do next? Well, one of the biggest advantage would be to version the serialization format, because this way we would be able to change it and do optimizations at code generation time that changes the serialization format. And also it would be great to eliminate the reflection from field selectors, because that can also give us very good performance improvement. And we could do better to guess what would be the size of the serialized object, because right now most of the getLength method of the serializers are very dumb, because there are very little code in Flink that uses this information, and there are very little code in Flink that uses this information because most of the serializers don't really do much to guess this. So in the long run, it might improving this information might give us additional performance benefits. And once we will be able to eliminate redundant null and subclass flags, we can only do that once the serialization format is versioned. Then the serializers that are generated for Pojos will have better performance than tuples. So basically, I also measured this. So I did an experimental version of this code generation where I broke the serialization format, and I was able to get performance numbers that are better than the tuple serializers. Okay, so in the distant future, we will have more freedom to do much more crazy optimizations, because we no longer depend on the JVM, and we can also do crazy transformations to the serialization format. For example, we could have columnar serialization format, and once we can do such transformations, the generated code might have better performance than the naive handwritten one. And also there are a lot of opportunities available, because the Flink type system does a very good job of preserving type information. So at runtime we have a lot of information that we can rely on and that we can utilize to generate very specialized and very performant code. So in conclusion, during this summer I was able to do a very significant performance improvement for Flink, at least I think so, more than 20%. And this groundwork with the code generation will enable much more performance improvement based on code generation. And actually this summer was the first time I used a JVM language, and this was the first summer that I worked with a big data project. I have a background in compilers and CNC in the CNC++ world, so I can say that dealing with class loader related issues is not a newcomer friendly way of introducing someone to the Java ecosystem. And unfortunately, it is not so the code generation is not part of mainline Flink yet, but it is very close to. Only some cosmetic changes left before it can be merged, and I'm happy to receive reviews. So I would like to thank all the help to my Google Summer of Code mentors, and also to Data Artisans for brainstorming, and thank you for your attention. And I'm open to questions in case you have some.
Hi, I can imagine why you did it, because in the times of the dynamic class loading and the serialization, it's just full of reflection and it costs you time. But the fundamental question I have is that you are still serializing your serializers in runtime, where basically when you deploy a model, you know what types you will have in the model. So why don't you do it at the design time that you create all the class loaders and instantiate them immediately when you upload your model? So why do you still need it in runtime?
So let me just make sure that I get your questions right. So you are wondering why the code generation is done at runtime and not at compile time?
Exactly.
Okay. So well, at compile time, we do not have all the information, because in the general case, even though it is not very frequent in Flink applications, I think, but in the general case, when we see the static type at runtime, that reference to the static type might actually point to one of the subclasses of that static type. Mm-hmm. So it is perfectly reasonable to do the code generation at compile time when we know that there is no subclassing involved, but Flink would like to support.
I understand, but at least for all the subclasses that have been defined, you could create in the compile time already your class loader, and your model would become a bit larger, but it would prevent serialization. And that you could still allow that if the class loader is not known, that you would serialize it in runtime, but at least you limit the amount that you do at runtime.
I see. Well, yes, that's true, but during the measurements, I did not really see much overhead because of the compilation. So right now, in order to get the best return of investment, it seems like it is better to concentrate on code generation schemes and then moving the code generation to compile time.
You said you used the free market templating engine in Janino to generate your code. Could you tell us the reasons why?
Right.
Why you didn't use direct bytecode generation with ASM?
Sure. So one of the reasons was that Janino is already used by the table API in Flink. So we at least it is better to have one code generator in the whole project, and the other reason is that it is easier. It turned out to be easier to actually generate Java source code than JVM bytecode for this problem domain, and it also it is also because of the way this templating works, I think the code itself is much more easier to read. So I think in order to generate bytecode directly, it would have involved much more work and much more coding.
Any more questions? No. Okay, that's it.
Then thank you for your attention.